for coming. This is the first talk of the season. You know, Saturday Science is a series of lectures that we organize in LSU and try to convince great scientists and Manos to take some time out of their really busy schedules and come here and share the exciting of what they do with all of us. We have 4 talks this fall semester. One in September, first week, one the first week of October, November, and December. So if you don't have the information, it's outside. You can see the schedule and the title of other talks. And I am really delighted that you are here with us. And today we have the great pleasure to have my colleague and friend, Manos Chatzopoulos. I have been trying myself.
Good job. 7 years now.
7 years now. Manos is from Greece, so we are both from the Mediterranean coast. And he obtained his PhD in Austin, in the University of Texas, right, 2013. And then he moved to Chicago as a Hubble Fellow, a prestigious fellowship. And then we were lucky enough to recruit him to the Physics and Astronomy department in LSU. And today he's going to talk about the stars exploring, right?
That's right. Thank you so much, man. Thank you for having me here. It's great to see so many young people interested in science. So I hope that by the end of this talk, you will fall in love with things that blow up in the sky, like I did a few years ago. So it sounds a little ominous, but what I studied, what I focused my work on in my day-to-day life at LSU, is looking at the deaths of stars. And we're almost at the Halloween time, right, when things are scary. We're looking at skeletons outside of people's gardens, things like that. You'll find out there's some really scary things out there in the space that happen after a big star dies. But even more so, what's fascinating about the deaths of really big stars is that they die in this very bright, violent explosion that we call a supernova that you can find from millions of light years away, really far in the universe. So I'm going to talk to you about those things, about massive stars, how they die, and what's the aftermath of stellar death. So, like my colleague said, and now I cannot use this, apparently it doesn't work, let's see. There we go. Like my colleague Ivan said, I'm originally from Greece, and we have a long tradition with astronomy when it comes to Greece, right? In ancient Greece, actually, is where astronomy was invented as a scientific discipline. People like Eratosthenes, Hipparchus were some of the forefathers of the astronomical field. And fast forward a couple of thousand years later, there's still Greeks that like to look at the stars, like myself, with slightly more complicated last names, as you can see. So that's who I am. Like Ivan said, originally from Greece, obsessed with the stars, and right here in Baton Rouge, Louisiana, still obsessed with the stars. So the first thing I want to talk about is something that you all have done in your lives, right? And I'm assuming every single one of you in this room has gone out in a beautiful, clean night. Occasionally, it's hard to find a clean night in Louisiana, but let's just say that you found one. And you look up in the sky. And when you do that very simple observation, something that human beings have been doing for the entirety of their existence, right? Look up the sky. It's the simplest observation you can do. Then you're presented with this fascinating view. Things like bright spots in the sky that look like stars, which they are. But when you look at those pictures, when you look at this image, you start to wonder, naturally, as a human being, like, why do stars have different colors? Look at that. That one is a red, very red star. But this one is very blue. This one is a little bit orange-red. Why are some stars bright and some stars are faint? How far away stars are? Well, as it turned out, it wasn't easy to answer that question. It took a long time for a scientist to come up with answers to those questions. Even the fundamental question, how far stars are, it wasn't straightforward to solve. How do you measure the distance of something so far away, right? So right now we know that one fact that we can present is that the sun, which is a star that you're all familiar with, our own sun, that enables us to enjoy the day and live on this planet, is one of those stars, one of the billions of stars in the Milky Way galaxy, in our galaxy. And there is billions, hundreds of billions of galaxies in the universe, each one of which with billions of stars. So do the math, there's a lot of stars out there in the universe, right? And as it turns out, our sun is kind of average in a way, which sounds sad because we love the sun, right? However, if you compare it with some other stars in our solar neighborhood, in our cosmic neighborhood, you'll find out that there are some stars that are way bigger than the sun. And one of those stars is my personal favorite, Betelgeuse. So not Beetlejuice, the new movie that's coming out in a few weeks, but Betelgeuse the star. It's actually pronounced, spelled different even. And it's not like if you say Betelgeuse 3 times, it's going to blow up. So don't try this at home. But if you want to find Betelgeuse, you can actually see Betelgeuse with your naked eye. You can go out at night and find this very famous constellation called Orion. It's very distinct in the skies with the 3 stars that go like this. Actually, I have a picture of it. It's this one right here. Those 3 stars, the Orion's belt, and here is Betelgeuse, this big red star on the west side of the constellation. You can't miss it. Now, Betelgeuse is very, very interesting because it's not just a bright red star in Orion. As it turns out, it's a star that's several times over the mass of the sun. It's a massive star. As it turns out, it's also an old star, way older, I mean closer to its final years than the sun is. Good for us, I guess. And as it turns out, it's also much, much bigger in size. And here's a comparative chart that shows you how our sun, this little white dot here, compares to some other stars in our solar neighborhood. And this is Betelgeuse. It's about 1,000 times bigger in size than the sun. So these are the kind of stars that I'm interested in. And as it turns out, these are the kind of stars that lead the shortest and the most violent endings. The shorter lines with the most violent endings. In other words, live fast, die young. It's kind of like a phrase I usually use in my class that allows you to describe the fascinating lives of massive stars. So, and I don't want to get too technical, but why do stars exist? Let's start with this simple question, right? Why a star exists? You can think of a star as a ball of hot gas, right? Very hot gas, and the deeper you go into that star, the higher the temperature, the higher the density. And if you want to have something stable for long periods of time, something that doesn't dissipate, explode, or something that doesn't collapse, then you have to have balance. You need 2 forces to balance each other out. So the sun, for example, has been around for almost 5 billion years. How? Why? Why do stars survive for that long? It's a constant battle between gravity that wants to squeeze the star downwards and collapse it, and pressure that's trying to keep the star, resist gravity, and expand. So long as those 2 opposing forces remain in balance, the star remains in balance. And for the vast majority of the star's life, that seems to be the case, but there are moments when this balance is disturbed. So the other thing that I want to bring up is, okay, now we understand why stars exist in the first place, the balance between those 2 forces. The other question is, why do stars shine, right? Can you see a bright spot in the sky that's several hundreds of light years away from you? It has to be very bright. What keeps a star shining for that long period of time? And as it turns out, it's this form of super energy. You may have heard about it, right? Nuclear energy. The fusion between atoms in the hearts of stars, where the temperatures are so high, is the source of light and energy that a star produces. The reason that stars shine is because they use this nuclear energy in their cores. And for most stars, that fuel is an element called hydrogen. Now, hydrogen is the most abundant element in the universe. 70% of it. So luckily there is a lot of fuel for the hydrogen for stars to burn. But just like fuel in your car, also fuel in stars runs out. And when that fuel runs out, this balance between those two forces is broken. And then something happens. So to make things simple, as a star ages throughout its life, to sustain itself, to keep shining, it needs to burn fuel. So it starts by burning the fuel that's mostly available, hydrogen. And then it burns it, it converts it into helium, which is the second heavier element in nature. And then helium has to fuse together to make an even heavier element, carbon, nitrogen, oxygen. We're all carbon-based life forms, right? So carbon is very important. You see where I'm going with this? As a star is aging throughout its life, especially a massive star, it fuses lighter fuel into heavier fuel over and over again. So in the end of its life, it looks like an onion. The same kind of onion you can buy from Whole Foods, right? Not quite, but it's very similar. Where it has different layers over time, because over the course of its life, it burned lighter elements into heavier elements, and the ashes, the remnants of those heavier elements, are further away from its core. So as you go from the outside in, on the outside of your star, the outer layer will have the lighter elements, and then further in towards the core of the star, typically you'll get the heavier elements, right? But as it turns out, now you understand, why stars live, why do they exist, why do they shine? We talked about this, but we don't quite know what happens after that, right? Is it still going to keep happening forever? Are you still going to be making heavier and heavier and heavier materials in the heart of this star for eternity? The answer, of course, is no, right? Because as it turns out, once a special type of element is formed in the heart of a massive star, and that element is iron, that you all know, right? Once a certain type of element forms, as it turns out, you can't fuse iron. It's impossible to fuse iron to produce energy. So this is the end of the life, essentially, of a massive star. The moment that they make iron in the cores, that's why we call it iron core, a ball of iron in the hearts, there's nothing else that can be done to sustain the star against the gravitational collapse, against gravity, right? So at this point, gravity is very strong, and the core of that star, going back to this picture here, the core, the iron core of this star starts collapsing because this balance is broken between pressure and gravity. And gravity wants to pull things inward, right? So this iron core starts to collapse. When something is collapsing, it becomes hotter and denser. Take something and start squeezing it down to higher densities and temperatures. It gets hotter and denser. At some point, something really weird happens to that core. And that is that it becomes so dense and so extreme that it leaves behind a remnant. In some cases, we call this a neutron star. It's a very dense star about the size of Baton Rouge. It's so small and so dense, but it has the mass, about the same mass as about 2 times the mass of the sun. So essentially, take the sun, just to make it simple, take the sun and squeeze it down to the size of Baton Rouge. Can you imagine how dense is this object? So these are some of the most extreme and some of the most dense objects in the universe, those neutron stars. But in some cases, the end is even more extreme. Nothing can stop gravity, and in the end you will have a core that collapses into itself, into something that's so dense that not even light is the fastest thing in the universe. Not even light will be able to escape. If light doesn't escape, it's hard to see. We call this a black hole. So the mysterious black holes that you've all heard about, that you're fascinated with, they make the news. Every time there's a scientific discovery talking about black holes, it's news because it's so fascinating. A lot of those black holes are created by the deaths of massive stars. So that's pretty cool, right? And as you find out, a lot of stars don't like to live in isolation, like humans. They like to find partners. So a large majority of these big stars, they coexist with a partner. that's also massive, which is what we call a binary star system. And as time goes by, both stars will eventually die out, leaving behind black holes. So you will have a binary black hole that in some cases will collide. Those black holes will collide, disturbing the fabric of space itself. How many of you have been to Livingston, to the LIGO Observatory? A few of you. There's room for growth. Great. So if you go out to this great facility, right here in Louisiana, 1 hour away from here, it's one of the premier gravitational wave observatories on Earth. This is a place where astronomers are trying to detect those disturbances in space that occur when things like black holes come together. The iron core of the star, of the massive star, collapses down and will make some of these really weird high-density things. But that's not the complete story, right? There's more things that happen with the rest of the star. So going back to this onion picture here, right? You got the core that will collapse. This red ball here will collapse to make a black hole or a neutron star. But the rest of the star is not necessarily going to collapse as well. It's going to explode, as it turns out, in all directions. And this is when you have a type 2, what we call it, core collapse, supernova explosion. So here is an animation produced by Space.com that kind of shows you a big star, kind of like Betelgeuse, a red supergiant blowing up following its supernova explosion. And as you can see in this schematic, you have what we call the supernova ejecta, the remnants of the outer parts of the star that are moving outwards with incredible speeds. In the center, right in the heart of this thing, you have this collapsing core that creates a neutron star or a black hole. So that's a schematic of how those explosions, kind of like would look like, an animation of them. Now, this is what we know happens because we find supernova. We find things that become bright in the sky and then disappear. We can see those explosions. But the question naturally is why and how bright those explosions are. How bright are supernova explosions? Remember, those are some of the most energetic events in the universe. To give you an idea of how bright they are, you could power the entire energy grid for 10 to the 22 years. That's 1 followed by 22 zeros. That's a big number if you were able to harvest the entire energy that's produced during the supernova explosion. Some of these explosions are brighter than their host galaxy. So in this picture, right here in the bottom, what you see is a spiral galaxy, and you also see a very bright spot right here on the right. This bright blue spot represents an explosion of a massive star, supernova. If you were able to collect all of the light from this spot and compare it to the light produced by the rest of the galaxy altogether, you will find out that there's more light produced by this explosion alone than the collective light produced by the stars, the billions of stars in this galaxy. This is how bright supernova can be. It can be as bright as 1 billion, with a B, billion times the luminosity of the sun. Like 1 billion suns. Very, very, very bright event. And you can think of it kind of like fireworks in a way, right? They become bright, and then they disappear. This is why because of things like supernovae, there's a whole field of astronomy that's called transient astronomy. Transient is something that comes and goes, right? It's temporary, right? So, in this case, you also have a transient phenomenon. Supernova is transient. It becomes bright and then it dims out. And astronomers observe that in real time. They point their telescopes and they're observing light from the supernova in real time. So what they can do is they can map out how bright a supernova becomes over time and then how it dissipates. So this is what we call, in technical terms, a supernova light curve. As a function of time, you observe how bright the supernova becomes. So it will get bright, 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 and then it will reach a peak brightness, and then it will start dimming out. Now, why are they important? Why do we care about these explosions? First of all, I hope I convinced you they're pretty cool, they're very bright, you can find them at large distances. In some of those cases, some of the most extreme objects in the universe are left behind following a supernova explosion. But there is another even more fundamental reason why supernovae are important. This is the fact that all the elements that you see in the periodic table of the elements in your school, not all of them, but a majority of them, of the heavy elements is produced by supernova explosion. So, going back to the onion picture, let's go back to the onion picture one more time. I promise you it's the last time I use the term onion. So, as you can see here, by the end of the life of this massive star, you have your iron core surrounded by other lighter previous fuels of the star. That's still locked into that star. It's still locked into that star until the star explodes. When the star explodes, all these materials that were produced during the star's life, silicon, carbon, oxygen, will be dispersed into space along with this explosion. And then on top of that, after the explosion, right after the explosion, the energy of the supernova and the light that's produced is so high that you can produce even more heavy elements, including radioactive elements, like plutonium, uranium, or nickel, cobalt, gold. Who doesn't like gold, right? So all of those heavy elements are, in some cases, there's other ways to produce them, but in some cases are produced during the deaths of really massive stars. And I'm focusing on those. So supernovae are important because they enable the seeding of those elements into the universe, right? And the fact that we're here, the fact that we live in this technical civilization, hinges upon the existence of those heavy elements that you see in your periodic table. So we're all, as Carl Sagan used to say, we're all made of stars. So the question then becomes, how do we find them, right? Like, think of the firework example. Those things become bright and then they disappear. So you have a very short window of time to find them. It's not like you have all of time to just look in the sky and be lucky enough to capture some supernovae. You want to find them as early as they happen. In the older days, that wasn't always possible, right? Because you do have, thanks to a lot of bright amateur astronomers that would look at the sky because they're obsessed with it, right? Would look at the sky every night. They would be able to find some of those events early on. But that's not sustainable. If you want to study the supernova in detail, you want to be able to discover them more effectively. So how do astronomers find supernovae? So Ivan said that I was a graduate student at the University of Texas a while ago. And if you go to the west part of the state, there is a big telescope called EBPRL telescope, which looks like this. Now, there's another smaller telescope there that kind of looks like R2-D2 from Star Wars that's called ROTC. ROTC stands for Robotic Optical Transient Search Experiment. The whole purpose of ROTC, and you can see this in action here, moving around. There was a movie that was playing earlier. I'm going to play it again. The whole purpose of this telescope is to scan the sky automatically and look for things that are new. And the way that it's done, it's fully automated. It's a robotic telescope. It's a little robot telescope, right? And the way that it works is by taking a lot of pictures of the sky and then going back and taking a lot of pictures at the same sites again. Why? Because if you do that at high frequency, you can detect things that are new in the sky. So if I take a picture right now of this crowd, and then immediately take another picture, and I subtract those two pictures from one another, I will be able to say what changed in the room, who moved, what difference, what happened. So by doing this, astronomers can detect things that are changing in the sky in real time. So if something starts to become brighter, they can capture it and now there's much more advanced telescopes than this. That was back in 2005, 6, 7, 8. Right now we have even more advanced arrays of robotic telescopes, and we're building even more of those that cost a lot of money to do this kind of job, to find those transients, those supernovae, as early as they occur. So modern day astronomers use robots, they use computers, they use very advanced techniques a little bit of artificial intelligence as well, as it turns out, AI, to discover those things early on. Then the question is, okay, if we find them, we observe them, we can measure how bright they get, we can get a lot of information about their spectra. How do we study them? How do we understand, like, quantitatively what happens when a massive star dies? How big is it? What kind of elements were produced during this explosion? Things like that. And as it turns out, modern day astronomers that study supernova and try to interpret supernovae, sometimes they use pen and paper, just like Albert Einstein did, but if you really want to push the envelope and make a groundbreaking discovery, you have to use computers. You have to model the lives and the deaths of these massive stars in some really powerful computers. And it's not the computer that you have at home. It's some of the strongest supercomputers that we have in this country and elsewhere in the world. So for example, this is what a supercomputer looks like. Kind of looks like a locker room, but it's a very expensive locker room. It's a $100 million locker room, right? Where you have stacks and stacks of processors, computer processors, hundreds of thousands of them stacked together, working together to simulate, realistically simulate, three-dimensional explosions of stars. Because we live in a three-dimensional world, right? If you want to understand how these things happen, you have to emulate them as well as you can. And it's very, very, very tough to solve this problem. There's so much physics, I'm not going to talk about the equations involved, but there's a lot of things that you have to solve to model how a star dies. And usually those type of simulations happen in places like this, with supercomputers. Now, it might cost you $100 million to install, but it costs you millions of dollars to operate as well every year. The electric bill for this thing is very expensive. It's not your energy monthly bill. It's a little higher than that. And on top of that, you need to staff it, you need to support it, you need people in IT to keep it running. It's a whole operation. So we use supercomputers now. So if you ask me what you do in your day-to-day life, at LSU, quite often I have to log into things like this from a remote distance from my office and start simulations on those things. So there's some other pictures of supercomputers, the Mira supercomputers, Stampede, Hobart, Titan, which are scattered across the United States. Now they have a bigger one that they built at Oak Ridge National Laboratory as well. Summit supercomputer. So then, now you know how we find supernova, you know how we study supernova. One more thing that I want to say here about supercomputers is the why. Why? Why do we spend all this money and time and run this very sophisticated computer simulations to understand supernova explosions? Because you do not have science unless you can interpret what nature is telling you. So on one side, you get those observations right here from like the ones I showed you from those telescopes, right here. This is what nature is telling you. Nature is giving you the signals, the measurements. You measure those things. Like you can measure the length of this table, you measure how bright the supernova gets over time. You measure its composition. Those are real things. But then you have to interpret those real things with a realistic model. So that's when you turn into these machines to try to create a realistic model that can match those observations. You only win if you really can match, if your models can match what nature is telling you. It's the whole purpose of doing this iterative process called the scientific method. Okay, so now I want to talk a little bit about the aftermath. So, all right, so you have a supernova, it explodes, it's very bright, a billion times the brightness of the sun. It's far away. The fact that it's bright and you can find it's indicative of the fact that you can find it at really large distances. What does it look like after it happens? So fast forward a few thousand or hundreds of thousands of years after the supernova explosion happens, what does it look like? What's left over? What's the remnant of a supernova explosion? Well, luckily, we live in the Milky Way galaxy where, like I said, there's hundreds of billions of stars, and many of those massive stars have already died in the past with supernova explosions. So in many of those cases, human beings actually recorded those explosions. Like the ancient Chinese civilization, for example, recorded one of these explosions, and then we went back to it with our modern telescopes and we took a picture of that remnant of that supernova. So we are lucky because in our Milky Way galaxy we can actually observe those things in high detail. So what you see here are some pictures of those supernova remnants. On the left you have Cassiopeia A in the constellation of Cassiopeia. And here you have the Crab Nebula. This is really cool. This is in a constellation of Crab. And in the center of this, if I were able to zoom in, astronomers have found actually observed one of those really weird, very dense, massive, leftover stellar remnants that I talked about earlier. A neutron star was discovered in the heart of this Crab Nebula. Now, I would caution you that when you look at those pictures, in reality the colors don't look like this, like from your naked eye. If you had Superman vision, and you were able to look at those things, you would see more like a gray, like a black and white kind of picture, grayscale. However, it is very useful for astronomers to enhance this and add colors, because colors give you some kind of information for astronomers. So where it's bluer, for example, it may mean that you have higher temperature material. Where it's redder, it might mean that you have lower temperature material. Or different types of material. So by using colors, by enhancing those images with colors, you can get a three-dimensional sense of the structure, the morphology of this supernova remnant. Why do we care? Because a lot of us operate under the assumption that everything is a spherical cow, as we like to say in physics. Like everything has a spherical shape, and it's nice and round and symmetric. But when you look at those things, when you look at supernova remnants, and I'm going to show you more pictures of supernova remnants, that couldn't be further from the truth, right? A lot of them are highly complicated and asymmetric. Why? Again, this is the basis of the scientific method. Observation, question, iteration, theory, validation. Right? Why? And you can see it. You can see it without even doing any measurements. You look at several supernova remnants and they have different shapes. It's natural to ask yourself, why? So this is another, again, picture, high definition picture of the Crab Nebula. And another high definition picture of the Cassiopeia. Now, let me steer your attention here to this one a little bit. I don't know if you can see it from all the way from the back, but there's some distinct features here. For example, if you pay close attention, there's this linear-looking feature on the left. It looks like some sort of jet is moving away from this explosion. What's going on there? Do explosions of massive stars produce jets? Right? What is really the nature of this? Right? And then it gets a little more complicated in some cases. So this is another one. I will caution you, this is not from the death of a massive star, as it turns out, because there's another type of supernova that I haven't talked about yet. But this one, is more or less round. Not perfectly round, but it's very patchy. It's like this cloud, right, with like a sponge in a way. And that one was discovered by Tycho Brahe, a very famous Danish astronomer. And then there's this one. Look at that. That looks like a football. That is not even round by any stretch of the imagination, right? This has a very elongated shape. And if you zoom into the heart of this thing, you see something weird. You see this disc with those kind of like jet-looking things coming away in opposite directions. One astronomer sometimes jokingly described as the bagel and breadstick scenario. You have a disc, which is a bagel, and you have a breadstick, which is little jets going in opposite directions. So again, why? Why do you have this incredible diversity in the morphology of those supernova remnants? As it turns out, what you see here, essentially, what's right here is another example of a pulsar, of a neutron star. This really, really exotic, high-density remnant left over from following the death of the massive star. Now, one of the things that I specifically like to look at is how stars, after they die, interact with their environments. This one is one of the most well-studied and most important supernova explosions of all time. It happened when I was 1 year old in 1987. Now you all know my age, I shouldn't have said that. But back in 1987, we had one of the greatest telescopes in orbit, the Hubble Space Telescope. So we were lucky because we could use the Hubble Space Telescope, the predecessor to the James Webb Space Telescope, which some of you may have heard about. It's the most powerful, advanced telescope that we have in orbit right now. Very expensive as well. So back in 1987, an amateur from Australia was looking at the sky and he noticed something new happening. Something seems to be happening at a region of the sky. Remember, this person was in Australia. So the sky in Australia is not the same as the sky up here in the northern hemisphere of the Earth. So as it turns out, have you ever been to the southern hemisphere? Australia, Argentina, South Africa? Only a couple of people. So if you go down, the sky is beautiful, as it turns out, from this side of the world. And there's two patches, bright patches of light on the sky that were observed by a navigator a long time ago, Magellan. So those two patches are called the large and the small Magellanic Clouds. Those are galaxies, those are like regular small galaxies that are neighbors to our Milky Way galaxy, and they orbit our galaxy. So this supernova was observed taking place in one of those galaxies by this amateur astronomer. And this amateur astronomer called up the scientific community and said, hey, something is going on, you may want to take a look at that. And thankfully, they did. So they turned some of the biggest telescopes, including Hubble, and they looked at the supernova explosion in great detail. Now, one of the reasons, which I don't mention here because I don't want to get too technical and boring, but one of the reasons why this is one of the most important supernova discoveries of all time is because they discovered a particle, a burst of a particle coming out of it, which confirmed our theory of how massive stars die. And I started this talk by talking about this theory, the collapse of an iron core. I use those terms. After the own instruction, you have the collapse of the iron core. And as it turns out, the prediction of this theory is that you will have a burst of this particle, this ghost particle called neutrino, that travels with the speed of light and barely interacts with matter. So as it turns out, they found some neutrinos when this supernova took place, which was further validation to the theory of how stars die. So that was another reason why this is important. But for me, what's cool is that we've been observing this supernova for 37 years since it happened in 1987. So, and if you look at it, what's going on here, right? There's a ring, there's a clumpy ring of material, there's this football-shaped thing expanding into this clumpy ring. Forget about, spherical cups. Stars do not explode as a spherical, nice, neat-looking thing in most of those cases. So let me play this movie again. Remember, this is a movie spanning several years. You can see the years changing here. And over time, you see this clumpy ring about the supernova get brighter and brighter and brighter. So what is going on here? What's going on here is that the supernova itself, the ejecta of this supernova explosion, is running into material, collides with material that was there before the supernova took place. That ring was there before that star exploded. And eventually the supernova caught up with it and started heating it up. That's why it got brighter. It collided with it and made it brighter and hotter. So what I'm going with this is that there's a lot more things that you need to consider when you study those explosions and the brightness and the light that comes out of those explosions. And that is the environment they explode in. Stars do not necessarily explode in vacuum, in empty space. They explode, they die within their own ashes. A star is losing mass throughout their lives. The sun, our own star, is losing mass as we speak. That is the reason why you can go out to Iceland and enjoy the aurora borealis, the northern lights. What you see when you see the aurora borealis is these charged particles that are leaving the sun, interacting with the Earth's atmosphere. So stars lose mass. This mass is not going to disappear. It's in some cases going to be around this star, right, when the star dies. So a lot of those stars, the supernova, are doomed to interact with their own ashes. Here's another one that, it's my second favorite object in the Milky Way galaxy after Betelgeuse. That is the EBPRL Nebula. So this one is very extreme. One of the coolest objects, actually, in the Milky Way. You can't see it in the picture, but if you were able to zoom into the heart of this thing, we think there's a massive duo of stars. Like you have two stars, a binary system of stars that are orbiting around another. One of those stars lost at some point, which was actually recorded in history. In the late 18th century, astronomers were looking there, and they found something happening. They saw that this star was getting brighter and brighter and brighter. So something was going on. Now go back to this location with modern telescopes, and it looks like this. So what happened is that one of those massive stars suffered an eruption that shed some of its mass around. And after this eruption, this mass created this nebula around these two stars, which we call the Homunculus Nebula. It's the EBPRL Nebula as well. And what's weird about this is that obviously it's not spherical. It's not a spherical shaft, right? It looks like a peanut-shaped thing. So you have the two opposite sides that look like two lobes, right? Or two different in the two different sides. So where am I going with this? First of all, look at what's going to happen when one of those stars explodes as a supernova. It's going to run into this material. It's going to interact with this very complicated environment. And that will affect how bright the supernova gets. This collision between a supernova and its environment can change the brightness of this event. In some cases, I was lucky when I started my career as a graduate student in Texas. They just had discovered some of the most luminous supernovae that were discovered up to date. Super luminous supernovae. The special category. There's only a few hundred of those that people have found today. Those super luminous supernovae, some of those super luminous supernovae, occur when a massive star dies and interacts with its environment. So some of the brightest explosions that we find are explosions that are becoming so bright thanks to this process, this interaction. Here are some other examples. Again, I'm giving you another picture of 1987A, which I showed you earlier. And as you can see, it can get pretty complicated around some massive stars. You've got some rings, you've got all kinds of bubbles. So, this is just to say that the environments around massive stars are dirty quite often. Massive stars do not often exist in splendid isolation, clean vacuum space. Which means that when they blow up, they will have to interact with this environment. Now, there is one type of supernova that I haven't talked about here. So far, I focused about these massive explosions, these bright explosions that are produced after the death of a massive star. A star that more than 10 times, 20 times, 30 times the mass of the sun can produce this explosion. But as it turns out, there's another way to produce a very bright explosion. And that is if you're hanging out with bad company. So to be more specific, if you have, like I said earlier, a large fraction of massive stars are actually with a partner. They have a partner. They're in a binary star system. So in some of those cases, you may have one of those stars that dies, maybe a smaller star that dies, leaves behind a very compact object, which is not as compact as a neutron star, which we call a white dwarf. So I don't want to get too technical with terminology, but this is another very compact remnant that's left over if lower mass stars die. But what that little thief is going to do is going to start stealing material from its companion star, occasionally throughout the life of the system, which means that it will start growing and growing and growing the more material it accumulates. At some point, it will grow so much that it can't sustain itself anymore. It will just explode. Those white dwarfs, they have a limit up to which they can grow, as it turns out. If you try to grow them beyond that limit, they will just explode. So there's another type of supernovae, which astronomers call thermonuclear supernovae, or type 1A supernovae, which occurs when white dwarfs explode because you push them over their limit by stealing mass from a companion star or by colliding with another white dwarf. There's different ways to do it. So, thermonuclear supernova, why am I talking about those things? As it turns out, it was thermonuclear supernova that led to one of the most important discoveries in astronomy in the 20th century. And just to show you a picture of what that looks like, here's another galaxy. You see this galaxy edge on from the side. And this bright spot that occurred back in 2014 is a type 1A supernova. Again, if you collect all the light from just this spot and compare it to the light that collectively is produced by the rest of the galaxy, it's very similar. It's fascinating, right? One explosion can outshine its host galaxy. So why thermonuclear or type 1A supernova are important? Well, those things are very bright. They're even brighter in many cases than the explosions of massive stars, by a factor of 10 or 100 better. And the fact that they're so bright means that you can detect them at really great distances. So using those supernovae, and the other fact that they're important is because they all come from the explosion of the same object, more or less the same type of object. White dwarf that goes past its limit will produce more or less the same brightness. So the fact that those explosions are more or less uniform in nature, and the fact that they're very bright, enables astronomers to find them at really great distances in the universe. By doing this, astronomers are able to constrain the properties of our universe at these large distances and determine things such as the expansion and the acceleration of the universe. So this major discovery of the 20th century, that we live in a universe that not only expands, but it undergoes an accelerated expansion, which led to a plethora of other side discoveries and hypotheses, hinges upon measuring distance in the universe. So astronomers quite often use these explosions to measure those great distances in the universe, and thanks to this study, we can constrain and understand how the universe accelerates, one of the biggest discoveries of the last century. And that research led to a Nobel Prize in physics in 2011, served between these two. So, I'm sure a few of you are wondering, you've talked about those explosions for this whole last 45 minutes. All you said was explosion, supernova, energy, right? So, should we be worried? Should we be a little worried? Should you lose your sleep that a supernova is going to kill you? Not right? So let's try to answer that question. So I will start by giving you the answer. Don't worry, you're good. Why are you good, however? Because as it turns out, stars are kind of like pebbles in a beach. There's way more smaller rocks than there's bigger rocks. There's way more smaller stars in the universe than there's bigger stars. Big stars are important, massive stars are important. They're the ones that explode as supernova. But only a small fraction of the total number of stars is massive enough to do that. Which means that there's not a lot of stars out there that can actually explode. Now, if you take that into account, together with the fact that within our solar neighborhood, if you look at the closest stars to us within a certain radius, you're barely going to find any that are massive enough to explode. And even when it comes to Betelgeuse, which we know is pretty big, pretty old, right? Betelgeuse, and we think it might explode within 100,000 years. I know that's a big number. Bear in mind, that's a very broad range. It may have already happened and we haven't seen it yet. Because Betelgeuse is 427 light years away. It takes 427 years for light to get to us from Betelgeuse. So if Betelgeuse were to explode tomorrow, it would be brighter than the full moon. It would be very fascinating to look in the sky at the constellation of Orion and notice this really bright spot getting brighter and brighter for a few days, weeks on end. But it will not affect us. It's too far away. So most likely, a nearby supernova won't kill us directly. Again, because of those statistics. However, there might be some other events that are tangentially associated with supernova, like gamma bursts and other things, that can produce enough radiation, if they're pointed towards the Earth, to briefly ionize the atmosphere, or even, in most extreme cases, remove the ozone layer and expose us to the sun ultraviolet radiation. So it won't be the supernova that kills you if that were to happen. Again, tiny possibility, close to zero. It would be the aftermath, like it would be the secondary effects. The fact that you're exposed to the sun's ultraviolet radiation because the supernova took away the ozone layer. So to give you the kill zone, a massive star will have to explode within 50 light years from the Earth to have that effect. And again, you don't really have massive stars that we should be worried about within that distance. So rest easy. I would worry about other things more than I worry about supernova. So what's the takeaway point? Massive stars that are 10 times over the mass of our sun usually die, and I say usually, I'll explain why, by this energetic luminous supernova explosion. Now let me take a moment to say, why did I say usually? There's a reason why I use this term. Because as it turned out, recently we found out that there are some massive stars that are so massive that directly collapse into a black hole. There's no explosion. So there is a survey, which jokingly astronomers call the survey for nothing, looking for stars that disappear from the sky. Stars that are there, and then you start seeing getting dimmer, 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 and then disappear. Instead of getting brighter, brighter, brighter by a supernova explosion. So, and we're still trying to understand, why do some massive stars, there's open questions here, right? Why do some massive stars, most of them, seem to be exploding as a supernova? We see supernova happening, I showed these pictures. Why do some massive stars collapse without producing a supernova? So the details of how supernovae occur still a matter of active study. And that's why we invest in this great infrastructure, these big supercomputers, to be able to tackle those fundamental questions. How do supernovae take place? Why do they take place? And to try to match the observations that we see. Now, obviously, I hope I convinced you that leaving this room, you have a little bit of love in your hearts about supernova, knowing that a lot of the massive elements that you use in your day-to-day lives are dispersed into the space thanks to the supernova explosion, or created during the supernova explosion. And the last item is, again, some of those things are very, very bright. So bright that you can find them at really great distances. Enable astronomers to study the universe at this really large scale. Study cosmology. Be able to understand why, how is the universe expanding and accelerating. So I want to close off. I started off by talking about my background, and I want to close again with another Greek, Plato. It is clear to everyone that astronomy at all events compels the soul to look upwards and draws it from the things of this world to the other. So I hope you're going to go out at night quite often for the rest of your lives and look at the universe and let me know if you see something. Thank you.
Thank you. So now we have the question. Go ahead. We finish all fast. Start collapse. The answer is milliseconds.
Very good question. So, a neutron star is still stable in a way. So, a neutron star actually, think of it as a ball, it's about the size of a fire. And the reason that it's still stable is a special type of pressure which is not available. And I don't want to get too technical, but if you squeeze particles together, try to force neutrons together, creates a freezing point with one mechanical exclusion, which essentially produces super pressure. This is not like the regular pressure. It's very strong. It's able to stop the blast. It's the last thing that can stop gravity from collapsing. Now, black hole is already going past that level. So not even that type of pressure can stop. That's light cannot escape on surface. That's the other thing. With a neutron star, you get something like escape.
When a star size, does it always result in some sort of black hole?
That's a good question. So it turns out there might be some, you're asking people. There might be some really massive stars that we think do not leave anything behind. They're so massive that there's a full-fledged explosion in every single part of the star is spread. We call those spread stability supernovae. So, yeah. That's okay, take your time.
How big is the star behind the event horizon?
So the event horizon is a concept that really is applied to, and Dr. Ivan Abdullah is a black hole expert in the room, but it's a concept that applies, and Peter, that applies to black holes. Essentially what that is the distance away from the black hole, right? That you still could escape from the black hole even if you go by the speed of light, which is the output speed you can develop, right? If you cross that horizon, you do. You're going in simple terms, right? So they don't quite relate for neutron stars. It's mostly something a concept of the first. Yes. Well, we don't quite know because occasionally you'll have neutron stars in binary systems orbiting one another, and in some cases they will coalesce, merge, and then maybe you will get them. Yeah. So depends, In some cases maybe you get them collapse if you have an external factor.
More questions?
Can start stabilize before it erupts and ejects a large amount of its mass and restabilize.
So that actually happens for some stars throughout their lives. So they will go through episodes where we call them outbursts or eruptions, like the Eden Arena picture I showed you, where they will lose a bunch of mass in a very energetic, bright event, but then they will settle back down to a state of equilibrium. But in the long term, you still have to burn fuel to keep existing. And fuel is going to run out, you're going to end up with a narrow core, and that's the end of you can't do anything nuclear physics. Yes?
Did our solar system come from one supernova or multiple, or do we know that?
I don't think I think there's still a little bit of debate about that actually. We definitely know that there was a historical supernova in the region. What we have done is we compared the abundances of elements that we find on our planet in the solar system with what you would expect from a star exploding in the neighborhood, and they seem to be consistent. But there might be previous generations of supernova that took place, definitely one at some point, the dominant one. But there might be some contamination with older ones.
Why do stars explode and become black holes?
Why do stars? Because they run out of fuel. That's the simplest way I can put it. Because to keep shining, they need to be producing energy, to be producing fuel. And if they can't do it at some point, then gravity is going to take over. It's going to start collapsing in the cores. So at this point, gravity is really the killer. It's all a battle against gravity. And when that happens, then their cores will either collapse to form a black hole, or a neutron star, but their outer layers quite often will explode into space. So, and that's really something that I hope you took away from this, is that it's only the central part of this massive star that will collapse and make those weird objects. The rest of it gets thrown into the rest of the space environment. I hope that answers the question. Or confuses you by one.
Have there been any black holes that have basically formed their most galaxies?
Not that I know of. There's some supermassive black holes. So, including nearby galaxies, astronomers, even more so in distant galaxies, astronomers have detected really big black holes in the centers of galaxies that are millions of times over the mass of the sun. In our Milky Way galaxy, there's a supermassive black hole that's about, I think, 2 million, 4 million, I forget the number, 4 million times the mass of the sun. It's still there, it's still doubling down, maybe a little bit of gas and stars, but definitely not the entire galaxy. So I don't think there's evidence that supermassive black holes have doubled down yet. Entire galaxy. Maybe in the early universe, the answer is different. I don't know.
So how are you able to determine that it's lead? These different elements, if they're out in space.
Great question. So there is a lot of power in light. So that's something that I like to talk about when I teach my class at LSU is, before I even talk about stars, I talk about light. Because for the entire history of astronomy, astronomy is not like biology or chemistry. We have the luxury of being in a laboratory to look at things in your own vicinity. It's not like you can fly out to villages to take a sample. But you have light. And if you understand how light works and how you can analyze light to measure physical quantities, you can learn a lot of things. So to answer your question, what we do is we take light from stars and we pass it through fancy prisms that we call spectrographs. So essentially we break light into its individual wavelengths and colors. When you do that, you can identify signatures of specific elements that block light at very specific wavelengths thanks to the very nature of the atoms. The atoms can only occupy certain energies, so if you find wavelengths, lines as we call them, signatures of those particular places, there's hydrogen, helium, carbon, oxygen, nitrogen. So astronomers use spectroscopy, fancy word, to analyze what composition atoms are.
Okay, let's thank Manos again for